All right. So Lillian was good enough to ask me to kind of give a history of electricity. Being I've worked across the field in it and dealt with electrical and electronics in my whole career. So I got thinking about some of the different aspects of it. And then I got thinking that as a theme, the electricity is invisible. We don't see electrons. We don't see the movement of it. We feel it, we interact with the results of electricity, but we don't see the actual electricity until I got as close and I found out there's a new capturing microscope, an attosecond, so 10 to the minus 18th quantum stroboscope that was able to map position of electrons with a strobe flash around the nucleus of an atom. And here, these gaps are showing the different levels of the electron energy around it. And it's kind of important because it changes how we view and understand the basics of nature, affects what we can do. So when I was going to school, I think you can see my cursor, and we were taught the orbits around the electron. You get quantum orbits and all those levels, but they were taught to us as looks like planets surrounding the sun. But now we're more into the probability region, where the electrons are spinning around the nucleus, and you only get a state of probability of where the electrons are. And hopefully I can tie that in and explain why that's important as we move along. So what I realized, said, you need imagination to really work with electricity at depth. We can hook up wires and get something flowing, but if you really want to understand what's going on, you want to understand fields and radiation, you need to have some good imagination, and it's a challenge, no doubt. So I still love this quote from Arthur C. Clarke, that any sufficiently advanced technology is indistinguishable from magic. And I wanted you to think back at the different stages as we go through and what the knowledge was at the time and how magical the different things that they were discovering and challenging to figure out. And of course, Arthur C. Clarke was a pioneer in suggesting the use of satellites. So taking way back to the Greeks again, it seems to be a theme for tonight's meeting, but the discovery of static electricity was done by Thales. And so he recognized that if you rubbed amber with animal fur, you generated something, and that was static. We now know that was static electricity. It was interesting that they also at that time were understanding magnetic activity with iron, how it was attracted to lodestone. But again, their point of reference was these four basic elements and a fifth element, ether. And I'll touch on and off on ether as we go through tonight, but it's a concept and it's been changing, and yet it still stays with us to a certain extent as we go through. So as we move forward, we went kind of past the Dark Ages, and we had William Gilbert, who was the court physician to Queen Elizabeth I in 1600, and he's recognized as coining the word electricity, going back to that Greek word for amber. He wrote it up at great lengths. Of course, it was in Latin in those days, but he did understand and talk about the concepts of electrical force, magnetic poles, and attraction. And he was recognized with a unit of Gilbert, but tell you the truth, I've never heard of it. And now the modern term used for it is amp turns. Going forward, we had the French mathematician Descartes, and he was describing light as a pressure wave. And then you get the medium where it was transmitted. What difference does it make? And that's kind of comes back to the connection of ether, where he came up with a modern term of ether. And they were trying to investigate the properties to understand different things about light and reflection and refraction. So a little background on ether. It's spelled this, with the A or with the E, or it was in times past was called quintessence. And they thought of it as a material that fills the region of the space, especially above our terrestrial sphere. So they were using that theory of ether to explain different things that are happening, speed of light, gravity, etc. In the 1700s, up until then, you couldn't do too much with electricity because you just rubbing cat's fur and that didn't give you much control on it. So through the 1700s, this ability to generate static electricity with wheels and different things, and we'll talk about this later, this was actually able to store electricity in laden jars, the old ancient capacitors. And it was kind of fun to find out at that time they were using electricity as parlor tricks. There was one of the famous ones where they had a young fellow suspended on a board with silk ropes to isolate him, and then charged him up with one of these machines, and then he could fly over feathers and they'd pick up. So you had this element of magic that was going on. And you look back through even recent history and how many times that people have used magnetism and electricity for healing or for the patent medicine, kind of the quack ones. So we're still not past doing parlor tricks with electricity, but you have to recognize that it can be a challenge. We move forward to one of the most significant scientists of the time, and was Sir Isaac Newton. And again, you're talking about trying to figure out, a space filled with something, with the medium. What do you have to propagate vibrations? Everybody, when they start off, typically uses the water analogy in electricity to understand a little bit of the movement. So movement of waves through electricity. So, they're looking for something that would propagate the vibrations. And he argued against it, being a vibration of the ether. He was thinking it was something else, not quite sure what it was, but had to try and find something that's capable of traveling through the ether. Just brought this because Stephen Gray was from the English Society in their scientific communities, but he did start to experiment with electrical conduction, and he was one of the first to use the idea of conduction and insulation and discovering this action at a distance with the induction, with electrostatics. And then we've got in 1733, I just fought for Charles Francois de Fay. He was the one that came up with the idea of two types of electricity. He had the positive vitreous electricity, and it just was an alternate term for positive. So that was generated by rubbing a glass surface with silk. And then they started recognizing that it was a surplus of something. And then you had the negative, and there was resonance. And I got a feeling it may have been because of the body that they're rubbing it on. So like a shellac or sealing wax surface. So they're kind of calling it a resonance surface. But it ended up using the term negative for the substance that was generated there. Finally, they started recognizing that it was a deficiency of electrical charge. And they also were paying attention to that difference between conductors, they called it electrics, and insulators, non-electrics. And they discovered that the charged objects, like charged objects, would repel each other, and unlike ones would attract each other. So they were trying to fool around with the idea that there was fluids of electricity, and they were talking a positive and negative fluid, and looking for those changes. We move forward to Peter van Moostenbroek. He was a Dutch scientist, and he shared that with this German scientist and clerk, that they invented the laden jar, which was the ability to store static electricity in a jar, which basically we now know as a capacitor. We call them capacitors. So it allowed them to have more control of what was going on. They could take and now store it so they could use it for different experiments, as opposed to just trying to rub objects around and get little bits. So typically they were getting much larger sparks and energy as they go through. We move forward, and Benjamin Franklin was certainly involved in early electrical theories and that, his lightning rods and that. Here, the classic picture of him, the idea that he had a kite out in a lightning storm, where they were exploring the connection between lightning and static electricity that they could get on Earth. And most of the ones say that he's around because he really didn't do this experiment in the lightning storm because it was too, really too dangerous. But he had a few principles of things, and conservation of charge. Basically the idea that the charge couldn't be created or destroyed, only changed or moved around. Again, they saw electricity as a flowing fluid, and he called the flow direction positive. But as an electrical engineer, it's always plagued anybody that starts off learning about electricity to find out that the conventional term of current moving from positive to negative on a battery is wrong, and that the current and electrons actually flow from negative to positive. So we have Benjamin Franklin to thank for that discrepancy. Moving forward, when they're trying to understand how electricity came about, you had Luigi Galvani. He discovered that if they connected frog legs to the static generating machine, they could get them to twitch. So he came up with a concept of animal electricity. And if you're into measurements and that, he had the galvanometer, a very sensitive measurement circuit named after him. So when I was thinking about it, to look at how the history of electricity came about, the recognition that people had by the community at large is a good testament to who had significant effects on the discovery of electricity. So we'll go through this here in a minute, but just to think that you started off with coulombs, which is the movement of current, the measure of the pressure, voltage, amps, ohms, Faraday, to honor Michael Faraday, inductance by Joseph Henry, Hertz by Heinrich Hertz, and magnetic field by Tesla for Nikola Tesla. So there really isn't a lot of basic parameters. So to get nominated with it, that's a significant recognition by the peers. Now, your history of Tesla people will recognize that he wasn't honored with this designation until significantly after his death in the 1940s. So still a major thing that he's got his name on one of the fundamental measurements in electricity. We move forward ran across to CharlesCoulomb. He discovered basically Coulomb's law, which is that the force between two charges is proportional to the product of the charges, so the amount on the charges, and inversely proportional to the square of the distance between them. Now that formula is the inverse proportionality is so pervasive because it defines gravity, electrical charge, so many things, that relationship. So Coulomb was honored by having the System International Unit electrical charge named the Coulomb. Move forward. Again, Volta, he invented the voltaic pile, basically the first battery that you could control. So now you're moving along so that you have electricity available on demand, as opposed to randomly collecting it with static electricity. So he proved that it could be generated chemically. He took dissimilar metals, and typically it was copper and zinc, with electrolyte in between them, and they were able to generate it. So he was disproving the Galvani's idea that electricity was only generated by living beings, the animal fluid. And he was honored with the electrical potential, which is called the volt. Now, Faraday or other ones might have been, but there was some political infighting, as usual, to decide who gets to decide it. And Volta's backers won out. One of the key figures in the history of electricity has to be Michael Faraday. He came up through the British Royal Scientific Institutions. He had a little formal education, that was always remarked in that class society of Britain, that he was able to be the son of a blacksmith, and he rose to be one of the most influential scientists. His inventions of electromagnetic devices that formed the basis for developing electric motors. And it really, because of his efforts and all the experiments that he conducted, that electricity became a practical use for technology. And he published the basis for these concepts and started off as electromagnetic activity in physics. This up here represents, there's two different forms of it. So you have the battery, and you have the conductors, and then you had a wire that dipped down into this pool of mercury. So, and then you connected the other wire to the mercury. So you had a current flow through the wires of the mercury with a battery in the center. And what happens was this wire in the mercury started floating around this battery in the center. Some things are a little sensitive. So that was basically the first form of changing electrical activity into mechanical energy. But they did lots of observations about the effects of current and magnetism and linking them together. And also his understanding of transformers and motors, and figuring out that changing currents in one circuit could affect a neighboring circuit. And then he realized that it really was, you had to look for another invisible thing, the idea of a change in magnetic flux or field. So again, you're kind of back to that magic when they started off and how they figured out and tried to envision and handle it. So he proved that electricity could be induced by changes in electromagnetic field. He wasn't a mathematician, but he did it by pictures and thinking, and he was the ultimate experimental researcher. And I was surprised, I didn't know about this, that he established that magnetism could be affected by rays of light, and that there was an understanding relationship between the two phenomena. And it looks like my note at the bottom is off the screen, but it says that he was honored by having the unit for capacitance, the farad, named after him. Up here represents some of the experiments in mutual inductance. You have a coil with a battery on it here. You have another coil of the battery. And they found a relationship that moving this coil, electromagnet, into this coil here, you could get an output. And depending on the speed you moved it, the rate of change of cutting the magnetic flux, you increase the current flow in the secondary circuit. So again, that's basically transformers, relays, solenoids. They're all a factor in these concepts. Here's an example of one of the motors that he developed. You had a copper disc, you had a magnetic field here, so the magnet would pierce here. You made electrical connection at the center and a connection at the edge, spun the disc, and now you could create electromagnetism. So, and he was working on that invisible concept of lines of force. And so the strength of it was by the number of lines of force cut by the conductor in a unit time. So, you know, because the outside could cut more than the inside, you could ended up developing a continuous current. So this is an electromagnetic generator, and it converts mechanical energy to electrical energy. So it was the start of modern dynamos. I think that because of this movement, they gave it the name dynamos, but we know them now as generators. I like this one. It goes back and ties into Nikola Tesla and his high voltage coils. But this was Faraday's idea of the cage. If you got a completely enclosed metal enclosure around you and you're inside it, the charge will stay on the outside, so you're protected. And we use that extensively even today for sensitive biological experiments, trying to get the cell voltages. They all do it in highly shielded Faraday cage rooms. If you're working on sensitive radios and you want to keep outside stuff from the radio, or you want to keep the radio from generating and interfering with nearby objects, you had that. So we had lots of those at the railway in every one of our radio shops. So that was the Faraday cage. I used the concept to channel electrical energy as it came to the railway tracks to try and protect from damaging the sensitive electronics inside it using a solid welded aluminum building. We moved forward and we had Andre Ampere, and he was again working on electrodynamics. You know, we now call it electromagnetism, but it's basically the same thing. Again, he was developing advancements in solenoids, and that was leading to the electrical telegraph. So he was honored with the measurement for electrical current, which is Ampere. You had George Ohms, and now he was, you know, one of the ones that brought math in, simple math into it. But this is the basics for all electrical activity. Ohm's law, where the current that flows is driven by the positive voltage as it's driven through a resistance, and you can determine the current with Ohm's law. Voltage is equal to the current times the resistance. It was, you know, that activity and the product, the strength of the circuit, and the understanding of the resistance. And then as we move forward in time, we got more and realized it was more complex than just simple resistance, and inductance and capacitance become involved in it when you're working in it. But this was the beginning of circuit theory. So he was honored with the unit for resistance, the ohm. We go on, and now we get into the mathematicians that got involved in it. And Poisson, you know, he was believing in the particle theory of light. And this is at the time when they were going back and forth between, was light a particle or was it a wave? You know, lots of conflict back and forth between the ideas in that. He was looking at transverse and longitudinal waves. And sometimes it gets confusing just trying to understand what they're talking about when they go through that. So, you know, the mathematicians, you know, they worked so long trying to understand that concept of the invisible ether. And this here just kind of represents, as we came forward at the beginning of the 1910s, 20s, where the double slit experiment, where we're dealing with wave-particle duality that we're trying to understand. So it brings into quantum mechanics, and so that they finally, you know, 50, 100 years later that, every particle or quantum of energy can be described as either a particle or a wave. Sorry, I got to stop this. Hopefully that did it. Okay. Then we move on. We start getting into the practical world of what electricity meant. And we had Samuel Morse in 1844. He was working on advancing the concepts of a single wire telegraph system. So you have the local coil to understand what's going on, the remote one to you transmit your messages across, your key to modulate the activity. And Morse was co-developer of the Morse code. When they started off trying to do telegraphy, they tried to have little levers that's moved to indicate which letter they were doing. But Morse came up with the idea of coding it, so the dashes on and off. So that led to the development of commercial use of telegraphy, and that really was the first major development of electricity at a distance. And what a difference that made to communication. You think back before that, unless you could physically pass something along by somebody moving, perhaps on horseback, they tried signaling from hills. But when they finally got so they could perfect the system of sending messages at a distance, it was this major change in the world around them. Go back, and you start delving into the history of electricity. You get into the physicist, James Clerk Maxwell. He developed and brought together theories of electricity, magnetism, and light. He wrote about them. He was looking at another concept, where it's light's moving in the same medium, and the linkage between electrical and magnetic phenomena. And it led to his prediction of the existence of radio waves. There's the magic. At that time, they didn't understand that anything could move through the atmosphere and be captured. And here he is, he's using his mathematics that he's dealing with to predict that they came about. And we'll see that they came farther down. And so he really is considered the founder of the field of modern electrical engineering. His equations are the background for it. Now, don't ask me if I can calculate all the equations in that. Once upon a time I did. But they are deep level. But they are fundamental for so much of the activity when you get into the deep level. So they were going through this time frame through the 70s to the 1900s, and they were hunting for a model that made sense of how the energy was transmitted. And so his equations were working on it. So then he had all these scientists that were doing brilliant work in the area. So I'm just popping you forward to continue the timeline of the electrical activity. And we have to recognize that in 1882, Edison, he developed the practical generation of DC electricity. Stayed about 120 volts was his maximum because he was scared of anything higher. But he did get this station working in downtown New York in the financial district, basically. And so he was demonstrating how you could build a complete system of commercial electrical lighting and power. We go forward and we come up with Nikola Tesla, who had dramatic different vision of how things can be done than DC. And he had that idea of the rotating magnetic field, the rotation being caused by alternating current. And then he figured out how to finally take and use the alternating current energy to generate mechanical energy. And that was the difference between whether it could be utilized for more than just lighting lights. So it went on, and Tesla and George Westinghouse managed to demonstrate to the world what the significance of electricity could be at the 1893 exhibition in Chicago. They had to beat out General Electric and Edison to do it. Edison blocked them by taking away the availability of his electric light bulbs for patent infringement. They had about 6 months to go through and produce a horrendous number of light bulbs. And they did it, and Westinghouse uses his commercial capability. He had a train that went from Pennsylvania to Chicago every day to send out replacement bulbs because his bulbs weren't as good as the Edison ones and they burnt out too often. But if you had a big enough supply, you could keep replenishing the bulbs and prove the practicality of the complete polyphase AC system that was demonstrated at the exhibition. So that went on, and they were just allowed them to compete for the right to harness the power of Niagara Falls and use alternating current to do it. And of course, alternating current, its main claim to fame is the ease that the voltage can be transferred with alternating current. You can step up and step down voltages. And then the higher you go on voltages, the less loss you have in the lines connecting it between. So it was that functionality that did it. And they used Tesla's patents for a large percentage of the machines used in Niagara Falls production. So here's the, a little later, here's some of the generators in that in Niagara Falls. And out here on the American side, you can see that the water was coming down through the stalks and coming through into these generators. So just going back, see I've covered off, we had the charge, the volts, the amps, the ohms, the capacitance to recognize Michael Faraday, inductance to recognize Joseph Henry, Hertz recognized Heinrich Hertz for the development of radio transmission or wireless energy transmission. And then Tesla did get recognized by having the unit of magnetic field named after it. I just want to throw this in too to realize what, again, the magic that you're dealing with. They were doing all this, and it wasn't until just after this that J.J. Thomson and Tesla worked on discovering that the electron was a subatomic particle. So now in modern theory, we're talking about in quantum mechanics that the electron position of the electron can be is represented by waveforms. And that again is magic to really fully understand what that means. And this idea that it's, you have to probabilistic electron density. So you get this, how we can represent where electrons actually are around an atom. We do know that electrons, they're now bound to it. The electrons, the free movement, you get the flow of charge, it's electrons that move. So that becomes your electric current. But as you get down into it, electrons don't move that fast. They're in the order of just millimeters per hour. But the speed of the current down the wire, or a conductor, is more like, 50 to 90, about 75% of the speed of light. So again, the magic of trying to understand how the velocity of propagation is different than the velocity that the physical electrons move. And it really did bring home that electron is the fundamental particle. So going back, I have to understand, we don't see electricity. We only see the effects of electricity, even lightning. When you have a lightning discharge, the light given off is electrons changing energy levels in the ions and the photons being given off. So you're not seeing the electrons move, you're seeing light energy coming off of electrons. And so we're just starting to be able to reach in and see the position. So that's why I kept re-emphasizing that blue circular slide. because it's such a new concept to be able to see that. I thought the concept of ether was dispelled in the early 1900s, but it's interesting as you read more and you start reading more, it says there's still some review of what's going on, how it's transmitted through space. Let you know that to visualize fields, it's always going to be a challenge. That's where the imagination, the mental pictures have to be done. To try and understand how the fields rotate around in a motor is pretty hard to do. Again, I talked a little bit, do we really fully understand how the electrons move when there's such a difference between the movement of electrons that we can count and the propagation? So there's waves that we're dealing with. We have to try and understand electron wave function orbitals around an atom. I know I just recently came across the idea of why is glass transparent? And some of the answers seem to be that the electrons around the glass are in a wave function that doesn't absorb the radiation that's coming in. Or the other answer is, why do other subjects, material, absorb light as opposed to transmitting it? Then there's always the case of trying to get down to the quantum level to understand matter. So conclusion is, electrical physics is fascinating. It's quite a mystery to delve into and explore.